excited we get to do this. And I know it's summertime here in the mountains, and I know we got the opportunity 2 weeks ago to go in the mountains a little bit there for a little bit of a run and hike. Is going into the mountains like something fun for you to do during the summer?
Yeah, definitely. I have really enjoyed the summer times here in Colorado. I think getting up in the high alpine environment and getting to run trails has really been a hobby I have enjoyed since moving here. I think this season's been a little bit weird. In past years, I've usually had like a summer trail race, and like every Saturday I've got a long run on some big loop in the mountains. And this summer has been a little bit different because I've been kind of recovering from an injury and then also writing up my thesis, so things have been a lot busier. But I've still gotten to have like some little escapes up into the mountains, and it just always really makes me enjoy being in Colorado. And summer is a great season overall, but particularly here.
Yeah, for sure. And I know injuries are definitely common amongst like people that like to go outdoors to do, practically anything, hiking or running or just any of like the high altitude sport. Like how do you think like the injury has like impacted like your running?
Yeah, I mean, for a while it made it not happen at all. What's interesting is it came right after a race and kind of after a season of having like a lot of races. And so I kind of already knew I was going to take this season a lot more chill. And so it kind of forced me to extend that like latency period of running for a while. I think longer than I would have liked, but it's interesting because I think at different times running has had more or less importance to me. And so for example, I was also very injured in spring of 2020. And on top of that, we were all kind of locked in and uncertain. And at that time, running was a really major outlet for me. Particularly in kind of clearing my thoughts and making sense of things. So kind of being in a pandemic, pretty much locked down and injured was like a really terrible mixture. And something I kind of had to work through personally and reprioritize like what place running had. What was kind of nice about this season is, I kind of already knew going into like these couple months that I was going to take a back seat, kind of wrapping up a lot of like career stuff with grad school and also kind of coming off of a really exciting race. It's like I knew it was going to be more low key this summer, but I didn't think it was going to take quite this long to recover. But the nice thing is I have gotten to really start running again, build up, and that has been really nice.
So I know you mentioned like grad school there. Like, do you think like running has like a parallel as sort of like a like a stress reliever for like grad school, because I know how like stressful it can be. Yeah,
certainly for me, I think running has always been something that I think helps clear my head. I actually saw a funny satire article title the other day that's like, woman runs to clear her thoughts, replaces all thoughts with I hate running. Which is sometimes true, but mostly not true. I think mostly what I find is running for me is a really good way to sort of like be able to have like a constant motion that I'm focusing on physically. And then it kind of like lets all of the things that I haven't really let myself have time and space to think about like come and like get sorted out. Can also sometimes be a prayerful time for me. But overall, it's nice because there's a degree of control as well to running, especially training. It feels like you're like really tangibly building towards a goal. You're seeing results. You're doing the thing. You're checking off the box. And that's sometimes the very antithesis of grad school, where a lot of things are outside your control. A lot of things don't work the first time. Timelines are never steady. And so I think it has been, when I use it healthfully, which I've had to like work through, you can find that balance of like getting to have more of these short-term goals that you get to achieve. That kind of helps balance out some of the stuff that's really hard to like be patient and kind of see the bigger picture as you work kind of towards goals in professionally as well. If that makes sense.
Yeah. And so it seems like you need a good amount of time, I would imagine, for the different problems that arise in grad school. Like what distances do you like to go typically?
Yeah, I have really been enjoying the marathon in grad school. That's something I tried for the first time my first year of grad school. And so I've really actually enjoyed that distance quite a lot. I have also done 2 ultras, like 50K, 60K, which are kind of a different thing altogether. They sometimes feel like a big day out in the mountains, with people like feeding you food and water every couple of miles, which is kind of nice. And then I definitely got started with more like half 10K stuff. And sometimes those are kind of nice because it's really hard to train for a marathon.
Yeah, no, I hear you.
Yeah.
Like marathon is like a really, really long distance that you have to like really commit to. Whereas like, maybe a 5K or a 10K, you can kind of do on the weekends. And maybe you're not going for speed or anything like that. Then you can, very... I don't want to say easily, but like it's achievable for sure. Whereas like 26 miles is like, okay, like let's set aside some months to like actually look at the diet and like sleep and like overall training.
It's kind of like your whole Saturday mornings for entire months are committed to it. And it's, and the risk of injury is like way higher with half marathon or with marathon and stuff as well. So they're just very different. Yeah. So
with like marathons, like do you tend to like train for them over like the summertime, or do you because like so we're from the Midwest and like sometimes winter is all you got to train essentially,
right?
And it's difficult. So I want to ask like if you're more of like a summer like marathon runner or like a winter.
Yeah, I feel like I have just been doing it long enough to barely start to have opinions about this because I've only done 6 or 7. It's like I have disproportionately done spring races. And part of that is my first 2 were the Colfax here in Denver, which is a great race. So that was sort of like my baseline of like, oh, I'm going to, do the local marathon. It's in May, so I'm going to start training in January. And you're right, it's really terrible because it's snowy and it's so windy. The wind is my nemesis. It's terrible. But then what basically happened is I really started training for Boston. I ran CIM in December in 2021, which that was a really great race. I did get a BQ, which was really wonderful. And then in the following spring, I had the Colorado Marathon, which had been a 2020 deferral. And so all that spring, I was like out there training, like never again a spring race, never again a spring race. And all of a sudden I was like, oh no, Boston's a spring race. So now I have done many spring races and I've decided it's manageable. However, summer and fall is much better.
Yeah. It's not like as heavy on like the lungs as it like as like a stressor, but I like to think that if you're training in the winter, it gives you like a better mental mindset going through it that others may not have if they're going through in the summertime. Just like a little bit more resilient, a little bit more gritty, just because what the weather does for you.
There's something about coming back from like a snowy or windy run and you finish, you're like, yeah, I'm tough. Yeah, and I feel more resilient about heat than I do cold because sometimes we do have like really hot Julys and stuff. So like a September or October race has its own challenges for training. But I did grow up with a lot more heat, and so I already feel like I kind of maybe have more resilience than most people to heat. But the cold has been a new thing since I've moved here. And so maybe it's partly doing those types of races have helped me feel tougher about the winter.
Yeah.
Because, if it's snowing outside, you still got to get it done. So, yeah.
Well, what does it feel like finally getting the BQ, the Boston qualifier there? Yeah.
It was pretty surreal. I think I've run throughout my life. Like I played tennis in high school and would run kind of to keep fit over the winter and stuff. And in college, I started to get a little bit more in like half marathon type distances and stuff. But especially like the first couple years of grad school when I realized I could handle a marathon distance, I wasn't super fast. I never thought of myself as super fast. I thought maybe like if I spend multiple years really working hard, maybe one day I could run Boston because I heard that was cool. And then I decided to at least try in 2020, which was the race I talked about that got deferred, of course. And, like there was no races for like a year and a half.
That was the year that you're supposed to go run for. It was in 2020.
Yeah, so there's a Colorado race in 2020 that I thought, I probably am not fast enough, but I'll try. Like maybe there was this on my mind. I was like, oh, I'll see how fast I can go. And then that's the one that got deferred. I didn't run it till 2022, and that's when I was like, I hate the wind. I hate the wind. But there were no races for a year and a half, and during that time, I got a lot faster. I kind of was running with really fast people, kind of getting pushed and stuff, and so when I did finally go for the qualifying time in 2021, I was more like, whoa, I never thought I'd be this fast. Which is a really nice feeling, I guess, because it's kind of one of those things where running had been something I had done throughout my life, but it had been something of more of like kind of a personal habit, something I liked to do when I travel. It had never been about the races for so long, and then kind of getting to like feel like I accomplished something with the pace as well was a really rewarding experience.
Yeah, I had some running with like a mentor coach, and he was telling us about his Boston experience, and he was just like, I'd rather have anything other than the wind.
Yeah,
because the wind was just so terrible for him, and his experience is that it's just like it's like running with a parachute on, and you're just constantly fighting this resistive force this whole time. Whereas like you can handle rain, you can handle snow, and then the sun is, like you would think that's like the thing that you would want, but a lot of times it's draining too.
Yeah.
But nothing like the wind.
Yeah.
So.
Yeah, maybe that's been one of the nice things about, training in Colorado is it's very difficult to get worse wind than we get here in the shoulder seasons. You kind of have like those, 20, 30 mile per hour winds throughout the spring and fall sometimes. And if you train in that, you can pretty much handle anything. Yeah. Yeah.
So I guess like what got you into running? Like other than sort of like the avenue for like a stress relief for like your PhD.
Yeah, I mean, it was something I did in like grade school to high school years as like a thing to stay fit, and because I liked it. Both my parents are runners, and so it was just something I like kind of did, when I wasn't playing tennis. And then in college, kind of caught a bit of the bug with distance because I had an internship in LA. So one of the ways I'd explore is I'd plan out a route, and I'd like go try out some restaurant or coffee shop, and then I'd bus back to the university I was working at. And so I just slowly started to explore more distances that way, and really kind of got excited. And towards the end of that summer, I did like a half marathon in LA. And I really thought it was fun. And so that kind of got me more excited about doing that. And I did some half marathons local to my hometown. And I tried to like push past the half marathon distance, but I would just always like completely tank around 15 miles. And then I met someone through my church group my first year of grad school, and she had just run a marathon. And I was like, oh, that's so cool. I always thought that would be really interesting. I can't do it. I just always get like completely tired at like 15, 16 miles. She's like, oh, well, what do you eat before you run? I was like, nothing. She's like, that might be your problem. Turns out it was my problem. A lot of the times I like struggle if I get up early to run to eat anything because I'm just not hungry. My stomach's not ready.
You don't eat any breakfast before?
Oh, no, I do now.
Okay.
Yes.
Okay.
I didn't then.
Wow.
Yeah.
That's impressive.
So looking back, it's wild because I would do like half marathon races and I would maybe eat a banana.
Okay.
Especially with more like races, I would usually try to get up early enough that like I could kind of wake up and get my stomach ready for food, but not for training runs. Like it was kind of one of those things that like I like to sleep too much. My stomach wasn't ready. So I just like run 10 miles without eating anything. It was really dumb. I don't know how I did that.
Do you feel like the jitters or cold? Because I know like when I do workouts like on an empty stomach, I get like these like tingling, like the tingling like sensation going through your arm, and I think that's just like low on like sugars or like necessary fuel to like actually go. Like do you ever feel that like when you don't like have anything in your stomach beforehand?
It's a great question. I think I've gotten a lot better about figuring out like what my stomach can handle early, what time I need to get up in order to like, you know, be able to fuel properly, what stuff I can eat while I run.
Yeah. Because I've run in the past where I was like, okay, I've had breakfast. This should be good, right?
Yeah.
I can go for as long as I want now, right?
Mm-hmm.
But then like in the middle is when I, you know, sort of discount like gels or like half a banana or something.
Yeah.
Just a little bit to get you going. Do you use like any specific fuel like during your like marathon trainings?
Yeah, I hop around a couple different ones. I really like Morton and Spring. They're very expensive. So I usually get some other ones for like the bulk of training, especially if I'm training for a marathon and I've got like multiple, you know, almost 3-hour runs. I do really like the gels, those in particular, but especially when I first started running, I just felt like it coated my whole mouth in sugar. So what got me started, when I realized I had to eat and I didn't want to, what I really started doing was the gummies. So I would do like, you know, whatever brand of gummy and like make myself have 2 every 2 miles. It's like very manageable. It's just a little bit and I could just keep it going. It really does make a big difference. Yeah. And I think a big part of it is figuring out what you can make yourself eat too. I think some people have an easier time with this, but like when I'm running, my stomach's like, no, nothing, please.
Yeah.
Yeah.
I hear that. Have you ever tried like the Martin?
Yeah.
Martin gels?
Yeah.
They're like the premier
I like
gel.
them a lot. Yeah.
And I only found them when doing like triathlons. They would like after you register and like, you know, give obscene amount of money for your registration fee. It comes with like a Martin gel pack. I was like, oh, what is this? I've never tried it. And it's like a clear gel.
Yeah.
And I was like, oh, okay, this is fancy, right? Because it's supposed to be like nothing, right? It's supposed to taste like nothing. And so like for you, like least like minimal impact on your stomach as you're going through.
Yeah, no, I like that one a lot. I think that and Spring have been the most helpful to me for sure. Yeah, they're very expensive too, but like I'm speaking as a grad student too, so I think about this stuff way too much. But I do really like it, and especially I think it was Kristen who first turned me on to them. She was like, "Oh, you gotta try it."
Yeah.
And then I was signed up for like a majors marathon, and they like they didn't give me a free one, but they did give me a pretty good discount, which is probably fair because I feel like the triathlons are a lot usually steeper registration than the races.
It's not free. It's definitely not free.
Definitely not free. No, but so yes, I tried and I was like, oh, this is great.
I look at it similar like going on an airplane and then like getting a meal. It's like, okay, you paid for the plane ticket in order to get that meal.
Definitely.
Sort of similar to that idea. But kind of going back into the mountains there, like, so I know running, both sources for you, sort of like road running and kind of like mountain trail running, is something that you really like to do. Do you also like do you also just like camping in the mountains there?
Yeah, definitely. My husband and I both really like to backpack as well as some car camping. I don't know, I really like waking up in the woods. There's something pretty great about it, about getting to like just go up and be in this beauty. Running and hiking through it, you get to see quite a lot, and it's very beautiful. But camping has got definitely a soft spot in my heart too.
Yeah, it's really like camping, like car camping or like backpacking?
Both.
Okay.
Probably more backpacking, I think. Part of it is my husband really likes to fish. And so if we can kind of combine all of our hobbies by backpacking to a lake, and then he fishes and I run. And so we kind of get like all of our hobbies together at once, which is nice. So I think we tend to favor backpacking over car camping. But when you car camp, you get to bring a pillow. So that's pretty sweet too. And you usually have a little bit nicer dinners. So there's some major pros there as well. Usually not quite as remote, but still quite fun. Yeah,
it's luxurious to see the people with like full RVs going by.
Oh my goodness, yeah.
They can have electricity. Yeah. And so it's quite a luxury that like you don't really think about until you start like backpacking and you find out like, oh, okay, maybe I shouldn't have like so many luxury items at me going through because
Yeah.
it's heavy.
It
like
is.
going through.
Yeah, you kind of have to pick and choose what's worth carrying on your back. It's pretty wild.
Yeah. So it's interesting that you talk about fishing there. This weekend we technically did some fishing ourselves.
Yeah.
Which was really fun because we I don't know what was wrong with the trout that we were seeing in the lake there. I don't know if it was like getting blown by like the wind, but he was just like really slow moving. So I was able to like kind of reach in and just grab him.
You just grab him.
Yeah.
That's amazing.
No poles or anything. But I'm imagining when you guys go, you guys have like full gear and poles and everything. So I have a question on like the fish. Do they usually like are like morning feeders or are they like evening feeders?
Oh, that's a great question. So this is all secondary. This is not my hobby. This is my husband's hobby. However, I have been listening, so we'll see how I do. I might have to fact check this later. I think that tends to go in cycles. And lake versus river is also depends. Like I think there's different patterns. My understanding is there's a lot of factors that change when fish like to bite. A lot of it's the weather, some of it's the depth of the lake. A big part of it is what's going on with the bugs. When the bugs are hatching, they're like way more active in biting. And so I think what often happens is depending on what the bug cycles are doing, that's what the fish will do. So I think morning and night is often like some of the best times to catch fish, but I think it also depends on the actual body of water too. And it's kind of fun too, because if you go into a fly shop, like oftentimes the people there will have more local information. So you'll kind of hear, people throwing around like, oh, what are they biting? Oh, we got to try nymphing today. Or I'm seeing what jargon is at the tip of my tongue. Should try this fly or that fly, because it's all really different. It depends exactly like what body of water you're at and what those fish tend to like and tend to do. I do think there are more like broader trends also, but probably not quite the expert on it.
That's fair enough. It's always interesting to run into like the people that don't bring meals backpacking, and they're like, I'm a naturalist and I'm gonna catch my dinner and like no backup. I'm just gonna fish, and then like if I don't catch anything, then I'll learn a lesson because the next time like I'll just get better or something at fishing.
See, that to me doesn't make a whole lot of sense, because it's not always your fault. We were backpacking 2 weekends ago, and we got up. We tried 2 different lakes, and in both, the fish were biting but spitting out the hook. So you would be able to get a hit but not set the hook. And this wasn't just like, both my husband and I tried. And we also noticed this with 2 other groups of fly fishers like on the other part of the lake. So it was definitely something that everyone was experiencing. Sometimes the fish are just really smart.
Yeah. And
so it's like, you do have an element of luck as to whether or not you get your dinner. So to like punish yourself for not catching a fish seems really harsh, especially if you're backpacking. That just sounds rough. One of these days it would be fun to catch our dinner. But neither of us are particularly skilled at cleaning a fish. We got to learn that in an environment that doesn't put our dinner at risk first, I think.
Yeah, it's a lot. You have to like have the proper gutting tools and like you said, to clean the fish out. And then also like you have to be sort of in a zone where you're permitted to have a fire in the first place.
Definitely.
Which is difficult here a lot of the times. And and if you pack it out, like if you have some sort of cooler, and so there's a lot that goes into like just maintaining and like treating and preparing your fish before. And so we ran into a lot of folks that were just catch and release, which I also have a question on that too, because it's like, isn't that bad for the fish to like essentially get a hook in their mouth, or is it sort of just like not painful?
Yeah, so it depends. A lot of hooks come with, so you've got the actual hook, and then you've got the like a little notch, a little blade. There is a name for that is escaping me at the moment. But you're supposed to clip those off in catch and release. So the idea is that yes, you do like poke a hole in the fish's mouth, but it's a very small one. You don't actually rip any part of their mouth or anything like that. Because when you catch and release, you do want to make sure that fish is going to live, right? Otherwise, what's the point of releasing it?
Yeah.
And so that is designed to be a process where it doesn't like change the longevity of the fish's life or anything like that. Otherwise, there wouldn't really be any sense in releasing them.
Yeah, I've heard it sort of equal to like a piercing.
Yeah.
Which is mind-boggling to me as well. It's just like I don't know why people would do that, right? Well, I understand like it's for like the aesthetics and like maybe it's something near and dear to you, but to me it's just like, wow, that looks really painful. Right?
Yeah. I mean, I suppose it's less painful than getting eaten, though. And, like, there's a big difference between, like, when you actually have the full hook that might actually kind of tear a bigger, like, piece in the fish's mouth. Like, that might actually affect their ability to, like, eat and survive later. It's like a piercing is not dangerous. Would hurt, but at least they're not. At least they're going to survive. But, yeah, it's true. I did pierce my ears in junior high. It's a little painful. It wasn't too bad, though. But I hear it depends on how sensitive the part you pierce is. And I don't know how sensitive a fish's mouth is.
Yeah. Well,
yeah.
You're stronger willed than me.
Thanks.
So I want to come back to more of the PhD process there. So from what I'm hearing, you're nearing sort of the end of your PhD process there. So I guess just to kind of start from the beginning there, you mentioned that you were in ion trapping research.
Yes.
Right. So for those that don't know, like, what is ion trapping?
Yeah. So what it is pretty simple, and then what it's for can like vary wildly. So ion trapping is a lot of what it sounds like. You're trapping ionized molecules or atoms, which is simply to say that we're talking about atoms on the periodic table or molecules comprised of those atoms that are either have an additional electron or a missing electron such that they have like a net charge. In my case, I'm working with both atoms and molecules that are missing one electron and are singly positively charged. So something that is charged by definition will react to electric fields. And if you manipulate these electric fields right, you can actually just sort of squeeze a bunch of ions or positively charged ions into a small space. And like charges repel. And so they do not want to sit closely together, but if you create like high enough fields, you can really cram them in decently close. And this is done for a variety of reasons. But you can incorporate other tools, in this case, something called laser cooling, to get those ions really, really cold, almost to like a quasi-crystalline structure or plasma. And then you're able to basically get those ions nice and cold and dense and do chemical reactions with them, which is what I'm interested in. But people use this for a lot of different stuff as well.
So like for chemical reactions there, does it apply, like do you use it to apply to any specific industry, or is it more like generalized?
This is more, what I'm working on currently is more fundamental research. A lot of it is trying to really understand foundational principles of chemistry. So by working in a really cold environment and also getting things in a very low pressure environment, like a very high vacuum, you're simplifying a lot of the different variables that could affect a chemical reaction. When you think of like general chemistry and like beakers and liquids and stuff, you have so much stuff going on. You've got lots of energy because it's warm. You have things in liquid that are interacting with all the solvents they're in. You have a lot of processes that impact the way the chemistry will go. And this has been very well studied as well. People are very interested in it. But when you're starting to ask questions like, what does it mean for a bond to break? You have to talk about much simpler systems, like things that are gaseous and cold. So you can really start to control what variables can affect a reaction and then kind of unravel the different building blocks that influence those processes.
Okay.
And so that's kind of one part of what we're interested in. The other part is these conditions under which we're doing reactions are very similar in many respects to chemistry that occurs in the interstellar medium and different areas of space. And so by kind of which molecules we choose to look at and study, we can kind of help contribute towards people's models of chemistry that occurs in space, molecular clouds, different areas. and try to help people understand why we have certain molecules in space.
I know that you're saying like it's really cold environment that this process happens in. Is it because in like warm environments it's too like finicky and like the data is not reliable?
Yeah, finicky isn't quite the right word. What it comes down to is, especially when we're talking about molecules, you know, you have multiple atoms stuck together. So there's a lot of different types of motion that can occur within these molecules. So you can have vibrational motion, you can have rotations, and then you can have translation where it's kind of moving all around. And temperature is very closely associated with how excited all of these degrees of motion are. So if you're trying to ask questions like, you know, how vigorously this molecule is vibrating, how does that impact a reaction? If you're really warm, you have essentially a lot of unknowns, or a lot of, what's the best way to put this? You have a lot of uncertainty as to how those degrees of freedom or how those types of energy might impact your reaction. So it's not so much finicky, because you can kind of use statistics to model all the different types of motion you'll probably have, but you can't really say anything about how all those different states might impact the reaction. So it's more simplifying the different ways that energy can impact a reaction by working colder. Does that make sense?
Yeah, and it's just kind of like seeing like the different types of outcomes that come from that.
Right.
Like, whereas you may not be able to get the same results in like a warm environment.
Yeah, in fact, you won't. And that is part of the interesting thing too, is it's basically essentially trying to study how energy impacts reactions. And so to some extent, you have to like slowly remove energy until you get to your simplest case. And the warm stuff, you know, the room temperature chemistry is fairly well studied, because a lot of those tools have been available to us for decades. But what has been pretty extensively developed in the last 20 or 30 years is a lot of the ways to get cold. And so trying to understand how these types of processes change as you get colder is sort of this new frontier of chemical physics that is part of like what my research is trying to explore.
I know you touched on sort of like the space or interstellar medium connection there. Was that sort of what like drew you into the process of ion trapping, is because of that application?
Yes and no. I think both the chemistry aspect and the space aspect, because when, you know, I'm in a physics program, a lot of my colleagues and people in my cohort are more pure physics research, and this is definitely much more of a hybrid. But in college, when I was studying physics, I definitely thought molecules were interesting, that a lot of these chemical principles and how you get different intersections in physics and chemistry are very interesting. So that was probably an initial draw, because I think a lot of the interstellar chemistry is a lot more of the like applications and like the people we're hoping will find our results useful, and a little bit less of what I work with day to day. That being said, I have always found space very interesting and very inspiring. I like, you know, one of my favorite memories back in grade school was getting to go to Cape Canaveral during a family vacation. And so one thing that I like shamelessly exploit is the fact that when I give talks about my research, I get to use like pictures. I get to use, especially now with a lot of the fabulous like James Webb Telescope images, like they're so gorgeous. And that is something that has definitely been an initial draw to science. So kind of getting to come back more so accidentally back to some of those applications with this research has been very cool. Because it's definitely felt a little bit like coming back to my roots.
Yeah, the James Webb Telescope was like this huge thing that had happened, and like kind of getting to see the results come back, getting to see those images, and especially being able to compare them to previous, the Hubble, is really amazing to see like the newfound clarity and like the details in it. Have you seen those images?
Oh yeah, definitely.
Yeah, and like sort of like the different discoveries that it's able to find, whereas like, you know, new galaxies or like star formation. And like that's just really mind-boggling to be able to see that technology grow. And so like for the research here in ion trapping, do you ever like have particle come from like, I don't know, like an asteroid or like a meteorite, and like do you analyze that?
So no, we don't get to use anything from space. Yeah, a lot of it is much more like, you can almost think of it as like a physical simulation. We're trying to recreate very similar parts of the environment in a lab. But what's pretty incredible is a lot of the important molecules that are known to exist in space are also things that we see and use, like here. Like I'm trying to think of, I would like to start naming chemicals and molecules that everybody knows, but I realize that everyone has heard of this molecule is not always true outside of chemistry and physics. And for example, ammonia, I think most people are familiar. It's often like there's a mixture of it that's often used for cleaning and stuff. It's a nitrogen atom with 3 hydrogens, and it is a very important molecule in interstellar chemistry. It's been found in a lot of different molecular clouds. It's been very well studied, and it's something that you can like buy in a bottle and just put it in your chamber. I've done a lot of work with acetonitrile, which I don't think. That's the one where like, oh yeah, people know of acetonitrile. And now that I think about it, I was like, no, I probably had never heard of it before getting into the sciences. But it's one where, chemists use it all the time for different types of things. And so it's very easy to get, and it's important. It's been found in different parts of space where they're trying to understand how you get buildup of all these really complex molecules, and so it's something that we can just sort of put into our chamber and ionize and trap. What is pretty wild is there's a lot of molecules in space and a lot of really big molecules. They found Buckminster fullerene or buckyball. I think this kind of created a bit of a buzz in the popular science world for a bit, but 60 carbon atoms in kind of this really cool round hexagonal structure, and they found this in space. And so kind of in these areas where it's pretty low density and pretty cold, you're getting enough chemical reactions to create something that big and complex. And that's a big part of the mystery that people are trying to unravel is, what processes kind of take you from really simple atoms that we know kind of come out of stars to these really complex stuff. But amazingly, a lot of it's the same molecules, or maybe not so amazingly, a lot of it's the same molecules that we have here on Earth too. And they're all identical. They're all the same number of neutrons and protons and electrons. And so that's part of the marvelous thing is we don't need to take something from space. There are other experiments that tell us what's out there, and then we can try to recreate it here.
Yeah, that's really cool. And then so to dive deeper in your research, is it more like just for behavioral, like sort of like to analyze like the reactions more, or are you trying to find like something new?
Yeah, and I think really depends on the reactions. So some of the work I've done has been with this ion called CCl+, carbon chloride ion, and it's, for example, that's an ion where people have kind of been debating whether or not it is in the interstellar medium, and if it is, how important it is, if it even reacts with anything. And so one of the things that our group has done has been to react this ion with a couple other things that we know are really important and definitely exist in important places where we know chemistry happens. And so by seeing that those two pairs do react and create important products, and they actually react quite fast, now we can make a case for, well, if this ion exists, we know it definitely should be participating in chemistry. And so now that's kind of informing the community as they look for this ion in space, that like, okay, if we find this, we really need to know how much of it is out there if we want to accurately model like what it's doing and what ions you get from those reactions. Other stuff we study is a little bit more fundamental. Like we had a reaction where we reacted with 2 different versions of what's called 2 different isomers, where you have the same atoms, but they're in different geometries. And this is a very interesting part of chemistry because in some sense you would expect a chemical reaction not to matter the geometry, like just which atoms are involved should be the most important thing. But on the other hand, like geometry can really change the way a molecule behaves. And so when it matters, when it doesn't, how it might change a reaction can be very interesting. So we had a particular reaction we studied where we saw very different behavior depending on which isomer we're reacting with. And that kind of helped us understand better, like what are the different mechanisms that are contributing to which products you get and why. So it really depends on the reaction, what you're kind of going to find. Oftentimes we don't really know why a reaction is going to be interesting until we've tried it. But the cool thing about our setup is it's got a lot of ability to detect what products we're getting from the reaction. And so you kind of get a lot of information. So you can just try doing reactions and see what comes out and try to make sense of it.
Cool. Yeah, and I know we've been more sort of like in the academic sphere here, but do you think there's as much research going on like in industry as well?
Not probably at this phase, because one of the more more industrial applications long term would be for something like this is really understanding chemical reactions to the level that we can control them. So if we can really understand energy in this type of vibrational energy but not rotational energy makes the reaction go this way. If we can really pare down and understand reactions at the fundamental level, then we can start controlling them in a way that we can change their outcome. And that type of ambitious science would be the kind of thing that I think would really impact chemistry, and especially different parts of industry. That's pretty far down the line. I think a lot of what I'm doing now is definitely much more more academic. I would like to start to see work that ripples more into applications. But I think right now it's much more focused on just trying to understand different aspects of astrochemistry and fundamental chemistry better.
Trying to toe the line between astrochemistry and chemistry there. Like, what is like the biggest thing that you see like from ion trapping that like impacts either one of those?
Yeah, I would say so how what I'm doing impacts those two fields. Yeah. So as we're measuring these reactions, as far as the astrochemistry stuff goes, what we're really hoping to do is to measure what products you get out of really important reactions and how fast they go. And what people do with this information is they look also with measurements that have been made by like telescopes and satellites and probes that measures what molecules are in different parts of the interstellar medium and how much of them there are. There is a space too. And they basically try to model how you build up to like the current conditions. So it's really trying to understand like, how do you get the chemical environment of our atmosphere? How do you build up different complexity of molecules in regions where stars are forming? It's trying to really understand the cosmos better. And it's using information that has been directly measured, both by us and as well as like actual observations in space and putting all those pieces together. On the chemistry side, it's a lot of it is trying to understand reaction mechanisms better. So it's trying to understand like if molecules are rearranged in one geometry versus the other, how does that impact its ability to like get pulled in by an ion? How will that make the speed at which a reaction tends to occur go faster or slower? How does changing the weight of these different parts of the molecule change that? There's a lot of things we understand about how chemical reactions work and a lot we don't. So especially when we find chemical reactions that don't behave as we expect, those are often the most interesting and groundbreaking in the field because it's kind of illuminating the parts we don't understand about, when two things come together, they have to exchange energy, they form a bond, they break bonds. And some of that is understood, but a lot of that is not. And so by finding these cases that we don't understand, we're really blowing up, pulling a microscope over the areas where we don't fully understand what is actually occurring in these processes.
Yeah, and with so much research, like how long is like a typical like PhD process in specifically like ion trapping? Yeah,
and so that definitely depends. I'm one of the few people I know that's using ion trapping for more of the chemistry side. A lot of it's being used in physics, especially for more of these like quantum computing type applications and stuff. they're all plagued by technical difficulties. Because what makes this much more of a physics PhD than a chemistry and astrochemistry is the fact that all of the technology we're using has been very well developed by the physics community. But it's also very like pretty novel technology, and it's things that actually can be quite finicky. And so I think most people are somewhere around 6 or 7 years.
Oh, wow. Okay.
Usually like it's more like 3 or 4 years of science and then 2 or 3 years building something that broke. Which is why, you come out of a PhD like that with a lot of skills. We joke around the lab that some days we're just plumbers. Because the amount of like water and gas pipes that you have to build in order to make the whole thing work is actually way more than you'd expect. But yeah, 6 to 7 years, maybe 5 if you're really lucky. But a little longer is pretty typical.
I'm just looking at it as somebody trying to like, perhaps looking into getting into the field. Like, I know like some physics PhDs can have a very like long like career in trying to achieve getting their degree and PhD and everything. Like I've heard some that are like, a decade long is not out of the question.
Yeah, that's not ideal for sure. I think a decade is usually a bad sign.
Oh, okay.
What's interesting is, so there's different standards among different professors on what constitutes like novel research. Because the idea is to get a PhD, you should be adding something new to the community. You should be an independent researcher, kind of capable of carrying on your own investigations after you get a PhD. And for some professors, that's like much more subjective. They're able to kind of assess a person, a project. And so, you might have 2 equally qualified people. One who goes right on an experiment that works right away. Another person who's like fighting the silliest technical difficulties for 4 years. And you get very different timelines out of those 2. Some professors are better at gauging like the balance of making sure their students get those novel results, but also appreciating that, shouldn't need a decade.
Yeah.
There are also some professors that I think really like that the longer you're here, the more skilled you are and the less they want you to leave. So sometimes those really long timelines can be an indication that the professor wants way more than an independent researcher out of you. When I look around, I think I do not see many cases longer than 7 or 8 years that aren't possibly linked to unreasonable management. But that being said, I'm only sampling one university, so
Gotcha.
I know this can be a long haul for a lot of people, but usually it's not supposed to take that long.
Do the professors ever start like a startup? Like ever spin like a startup?
Oh, yeah.
And then like kind of recruit the students that they already have and within their labs to go on through, and maybe that's why it adds some years into it.
Maybe. I mean, I think it shouldn't. It's where you start talking about things like conflict of interest and stuff. I think there's a lot of reasons people can take a long time, and sometimes students want to stay a while because honestly, it's a great environment to keep learning skills. Like, I mean, as a PhD student, you're, especially by the end, you can usually get a job that pays much better than what you're paid as a PhD student. So often that kind of leads to the conclusion, like, we're underpaid. And oftentimes there are a lot of stresses and a lot of really long work hours. But also it is an environment where you're doing a lot of learning. You usually have a lot of independence, and you're able to work with your advisor to find ways to research what interests you. So a lot of people do like to extend it, and so sometimes people are doing that of their own choice, which is great. But if somebody is staying longer because their advisor is starting a business, that at least placed that way raises red flags for me. But putting that aside, I think it is pretty common for professors to start businesses, hopefully in a way that doesn't take advantage of their students. And I think that there's a good percentage of successful companies in Boulder that have been started by faculty at CU.
Gotcha.
Yeah.
Yeah, and then I know you said you touched a little bit on an application for like quantum computing there as well.
Yeah.
And I know that's not related in your research there specifically, but sort of like I'm interested in like the process there.
Yeah.
It's like how it's different from what you're trying to achieve, because I think in that case for quantum computing, that ion trapping is they're trying to store information.
That's correct.
Within, right?
Yeah.
Whereas that's not what you're trying to do specifically.
Yeah, that's correct. There's some overlap in this idea of information, because you could look at this at some of the things I said about, you know, controlling the amount of energy and stuff as a way of saying like you're limiting the amount of places, you're limiting, see the best way to say this. When you start talking about getting atoms and molecules really cold, to some degree you're saying like you want to constrain the information about a reaction to a very limited set. You want to be able to say, you know, the atom must behave in one of these ways because it's so cold. And so in that sense, getting very cold and very high degrees of control kind of is always closely associated with information. But quantum computing takes this to another level, because you're truly trying to take advantage of very special aspects of atoms and quantum mechanics to get things into what you know, which like exactly what state an atom is in. So you're really trying to say things like, I know it's not vibrating. I know it's not moving. I know exactly like how much energy is in this thing. That way, if I change it in this way, now I know exactly how much it's changed this way. And so you can start playing games with it where you can have these atoms in what we call superposition, where it's in multiple states at once. And the relationship between those states is something that can be very well controlled. And that's part of what makes this type of computing appealing, is you're able to actually kind of do more processes with it than you can with traditional computing. And so on the long term, with once kind of a lot of the technical challenges that are going to probably take quite some time to work out, eventually you'll have something that is going to excel at the really big problems better than traditional computing. Yeah.
And you know, that's the application for that type of computing and quantum computing. But like for you, do you think that stems from like your general research on like ion trapping? Like that's where you're developing I guess like the IP or like the know-how for quantum computing?
No, actually, I think I would probably say the other way around. Or I would argue that the two of them kind of have like the same predecessor, because a lot of the ion trapping kind of started with different applications altogether, I would say. And out of the ability to control atoms and molecules at this level, I think both branches have really come out. It's been used historically for a number of different things. And the ion trap itself was like, when people first were able to like trap ions, that was a big deal. Like that was a big result by itself, not even using it for anything. Because it's actually very hard to trap charged particles.
Yeah.
They're actually very slippery. So, but it's been used and developed for a lot of fundamental things. And I would say, if anything, both quantum computing and like chemical applications of it have been like later grandchildren of like even the original purpose of ion trapping. Which I think also just goes to show that you never really know what you're going to end up using something for in science. You know, people have always developed technology for one thing and found and vastly different uses for them. My favorite example of this is the World Wide Web was developed for sharing data at particle colliders in Geneva. It was like people just developed a way to link computers so they could share data, and like that has completely changed our culture and society. A lot of technical developments I think are like that. People made them for a specific purpose, and then they turned out to like really join together with other things in a really fantastic way.
Like the evolution of like some proprietary like study that grows into like so many different fields of what we use today. Like one of them is like what you're saying is in chemistry or astrochemistry, and then like you potentially can go into like, you know, computing fields like quantum computing. Do you think it ever like touches into like healthcare at all?
Ooh, it's a great question. There have been a lot of discussions with this like type of atomic physics for security. So one of the big, conversations I think happening right now, as far as I understand in big data, is like, how do you ever certify something? There's random number generators, as they're used by computers, are actually not random. They're basically operating off of really sophisticated algorithms. So they're inherently predictable. And one of the places in our world that is not inherently predictable is quantum mechanics. It is completely statistical and random. And so people have been taking advantage of the fact that you can actually work with atoms in this regime where you're actually completely governed by quantum mechanics to build ways that you can actually use it as a true random number generator. I saw a talk on this 2 years ago. I'm not exactly sure. I think this is still a little bit away from truly being used in industry, but I don't think it's far. This kind of idea that you have like this random number generator service that really just can't be replicated because this is something that is not, causal at all. And so I could definitely see big applications for that in healthcare because I think security with medical records is a big deal. And so I think that's the first thing that comes to mind because I think of a lot of the direct applications of atomic physics being much more computative right now. But there are a lot of these principles and techniques that overlap heavily with stuff like MRI and such. And so I can definitely imagine it maybe changing the way we do some of those techniques and detectors down the line. But I am wading a little further away from my specialty, so I am definitely guessing a little bit here.
Sure.
Yeah.
For sure. And I think like just seeing what it's able to get into, like what kind of applications or industries or whatever you want to call it that I get into is like super fascinating.
Yeah.
Coming from like one sort of root principle.
Yeah.
Like experimentation or study or paper. Which I know like you guys spend so much time like creating these papers for publication. And like I guess just how is that process for like publication?
Right, yeah, like writing papers and getting them published and stuff.
It was just like the requirements, I guess, like in terms of like data or like experimentation or like it's just like what is that process like?
Yeah, there's a lot there. I feel like every subfield of academia has their very specific way of doing papers and what it includes and what the tone is. And I remember the first time I wrote and published a paper, I remember like reading it after. I was like, I barely understand this. Like sometimes it feels like we almost overcomplicate things. But at the same time, I think part of these papers is designed to be as like succinct and to the point and detail oriented as possible, which can make them really difficult to read if you're not in the field, but also very easy to read if you are, which is interesting because it kind of means it takes a while being in the field to really be able to read and write them well. The process is definitely designed around a concept that we call peer review. This idea that, whatever you write, if it's going to get published, it should be reviewed by other people within your community, within the sphere of specialty that you're working in. To sort of check the details, try to make sure you haven't made any like fundamental errors, to ensure that it's good science, to ask hard questions about and make sure that the process is clear. The idea behind anything you publish is that it should be reproducible. And so you should have sufficient detail to do that. So the kind of gatekeeping that is done in the community is basically if anything is going to get published in like a reputable journal, other people have to look at it and get a chance to ask questions and to verify that it was done well. And this is mostly good. What can also happen too, though, is you definitely you can get very different tones from different reviewers. Sometimes you can tell somebody's actually trying to help you do good science, and sometimes you can tell somebody might be a competitor that really doesn't really wants to like minimize the impact of what you're doing. So there are actually quite a few memes out there if you look on like it's usually under something like reviewer number 3 or reviewer number 2, where like there's sort of a trope where like you get 2 people that tell you your paper is so good and it's going to change physics and it's incredible, and the third person tells you it's complete crap and you're wrong. So this is something that happens often enough that the community makes memes about it. But for the most part, it's a process that's pretty rigorous and kind of stressful, but like often does produce like good stuff as well. It's actually something I've thought a little bit about lately, because there's been a lot of buzz about room temperature superconductivity. There's a group in Korea that has put a paper on the archive, which is not peer reviewed, but is often something that people put their papers on as they submit to journals, so that other people can kind of get a look in the months that process usually takes, as well as sometimes with something really large impact to help other people start like trying to reproduce it. But it's really hard to tell sometimes just looking at a paper if it's good science, if it's real, especially with something really high stakes like that particular application. But you can kind of see why it's like really important to have other people that have the same specialty also looking at stuff and trying to verify details, ask hard questions. But it tends to be kind of stressful too.
That's really interesting when you say you don't know if they're a competitor or their peer trying to build you up and sort of help you with your paper. It's sort of like the idea of getting scooped, right? Like you just don't know like which research group around the world is doing similar or the exact same topic as you. And you're trying to essentially race them to get to like you want to be first, right? And to whatever journal that you're applying to get into. Like, is that a stressful process to like not know like whether they're competitor or peer?
Yeah, I think it depends. I think my field has benefited from the fact that not many people are doing quite the same thing as us, and there's so many reactions to study. The likelihood that you would step on each other's toes is not super great. But also there is sort of this competitive aspect of like everybody wants to be doing really cool chemistry. So what's nice is I think getting scooped is not super common with that type of process, because if your paper is already in peer review, you've got a pretty good head start over anybody else that's going to try and do the same thing. But it can be frustrating sometimes when you feel like maybe sometimes people's comments are not necessarily about the science, they're just more personal. I don't know. Sure. And it's always hard to tell. It's all blinded, which is good. Some journals will blind your paper, which I think is a fantastic idea. It's usually not what happens.
And blinding meaning
like there's no names. So when you have someone review your work, you have no idea who they are. Sometimes you can guess based on their comments, their background. Sometimes they want you to put like 3 papers in the reference that are all by the same group. That's usually a little suspicious. But like you don't know who's reviewing your paper. Some journals then also don't let the reviewers know who you are. And I think that is a pretty nice solution as well, because that often does, it helps to remove biases for sure.
That sounds really great, like having sort of that anonymity factor. And so you're judging the work based on the merit of the work and not like the name or perhaps like I don't know if professors' names get tied or like universities' name gets tied to that as well, and I don't know if they're able to see that information, but just like just in absence of a lot of these like identifying information stats, like you can just kind of focus on the pure work itself.
I think that's supposed to be the point of it. And for all of that, I think people often do still put a lot of value into names, or, they have more conflicting opinions about younger researchers that haven't established themselves yet. And so even though ideally the process is supposed to be entirely on the merit, I don't think it always is. But it is hard, because even if you blind the names, these spheres in academia are very small. Like the number of people working on that have the type of apparatus that I would describe in one of my papers is very small. And especially if one of those other people is reviewing the paper, then they're like usually down to like 2 or 3 people. And so sometimes it's, almost a little silly to blind, which is I think why a lot of papers don't, is because most of the clues as to whose paper you're looking at are there if you want to figure it out. So maybe you should make people work for it.
Yeah.
I don't know.
Fair enough.
Yeah. It's a big systematic question, I'd say. Yeah. One thing I just really like is, it's a bummer none of this is visual, because I love doing lab tours and showing people like what the ions look like. Because part of how we get them cold is laser cooling them. And so what actually ends up happening is you can see the fluorescence that's emitted by a laser cooled atom when it sort of relaxes from one energy state to the other as part of the cooling process. And so you get this nice, really pretty looking crystal. And sometimes you can, when we load other molecules in it to do reactions, they create little dark bands because they're not directly laser cooled. And so you can sort of like watch the chemistry happening. And most chemical apparatuses, whether they're liquid or gas or any of the phases, like tend to be really fast. Like things happen pretty quickly. But because we're in low pressure gas environments, we slow it way down. So we're basically like slowing it down so that you only have 100 chemical reactions occur in like 5 minutes. And so you can literally just watch the chemical reaction happen one at a time, as like, where there's a dark band and your crystal changes. So I just thought that this was just super cool. You can just sort of watch the chemistry happen inside this pretty little glowing crystal.
Yeah, as like a visual to see. And like when you were mentioning on like the low pressure situation to kind of slow the process down, able to analyze it better, able to kind of see it better. Does it work when the pressure is high too, or like not in terms of like analyzation, obviously, because then it goes much quicker, I would assume. But like, would like the same process work in high pressure?
Depends. Yeah. So part of what is important about our setup that is true of space, and true of some chemical reactions but not others, is we're in a low pressure enough environment that you only ever have 2 body collisions, meaning that you have an ion and a reactant like meet, and nothing else is involved for the entirety of that actual chemical reaction process. When you start getting into higher pressures, there's some finite chance that a third gas particle is going to come along in the middle of that chemical reaction and change what happens. And this is part of the reason that people have done ion chemistry reactions for 50 years, but a lot of those early ones were really high pressure. So what would happen is you would have a chemical reaction that would get interrupted. And that's still really important because a lot of chemistry is higher pressure. You're still definitely learning something, but sort of towards that like theme of trying to simplify things and to limit any type of interruption from the fundamental process. By getting it down to a certain low pressure, there's almost no chance you're going to interrupt that chemical reaction with another gas particle. And so you're really getting to let the whole reaction take place and analyze those results without any complications.
Sort of like putting it in a vacuum and seeing how it would, theoretically behave rather than, more, what did you say? Like more like interruptive environments where you do have like sort of that high heat, that high pressure, and where you just have a lot more
factors,
and then more things that can go wrong with your experiment.
Exactly.
But that's interesting though, like to have it also work in that environment in those states too. Like I think that's what makes it like really ironclad and like makes it really hard to doubt that research if you can get out of that. But like I would imagine like maybe you want to keep it in these states, like this cold state and this low pressure state, just so you have control. Like you as a researcher, you as a business, you as a faculty or whatever, like you have the control over this reaction happening.
Yeah, and that's part of what is actually the next phase of this experiment that what I've been working on in the last couple of years has not been doing reactions, but actually building the next part of the experiment. Because right now, how we're controlling the temperature is trying to get it cold. But what we're trying to do now is actually get a knob that we can literally move so that we can actually change the temperature, both colder but also warmer. So that it's not just like, our gas must be anywhere from this temperature, or trying to use the right words and also it makes sense without physics PhD. You can say that your collisions have anywhere from this energy to this energy. And right now what we've been trying to do is like narrow that down by getting colder. But now what the next phase is going to be is we want to actually start moving that range. So not just being able to be colder, but also control exactly which energy range you've got. And so you can start seeing more directly what the change is as you move that energy around.
Oh, okay.
Which reactions get faster. Which reactions might give you more of this product than this product as you change the energy to hotter. And that really starts to get much more directly at the questions of like, how are these reactions occurring? What's most important to how they go, basically.
Okay.
Yeah.
Fair enough. Awesome. Cool. All right. Well, I want to hit back on the James Webb Telescope there.
Yeah.
I think that's really cool that you brought that up. Was there anything that caught your attention from James Webb in terms of like discovery?
Ooh.
I don't know if you've been keeping up or not.
Yeah, well, so I've mostly been following their Instagram and oohing and ahhing over the incredibly gorgeous pictures. Like I think some of the things that they've seen with just way better sensitivity that I can think of immediately are a little bit more, of course, is like, wow, there are a lot of galaxies out there. Like there's, and I don't want to, discount Hubble too, because Hubble gave us incredible images for multiple years. And then you zoom in on one dark section of Hubble and now you've got like as much detail as Hubble gave us in like that one small section. So I think that is, not been surprising, but like, certainly breathtaking is the amount of detail and the scope of what it's been able to see. It's been pretty phenomenal. That's the first thing that comes to mind for me.
Fair. And I think just like the journey too of it is really fascinating. Like sending it to space, taking, I don't know, however many months it needs to get up there, fully deploy. Yeah. And then even at that point, like you don't know what like space scrap is going to hit it or like some sort of like meteorite or something, or like some what is it? Like space impact debris that comes and makes an impact on it, and then like they have to troubleshoot from the ground and have to like fix it. I think it's just amazing. Yeah,
so cool.
And then on top of that, like I saw that it had like discovered a black hole. That I forgot which galaxy that it was in, but it was like a supermassive black hole. It was like a big black hole. And I was like, wow, that's really crazy that it's able to find that. Yeah.
Similarly, there have been pretty impressive improvements at LIGO. I don't know if you're familiar with this, but this is the gravitational wave sensor. They basically have two really long arms, like kilometers long, with really high precision lasers. And they can tell when the arms contract or extend because of gravitational waves, like literally like fluctuating space-time. And this thing is so sensitive and cancels out noise so well that they can actually see this type of changes. And they found two black holes colliding, I believe, as the first event back in 2017, 2016, somewhere around there. Okay. But they have made some really impressive improvements to the sensitivity, and now I think they're going on like tens of events that they've been able to see now. Just so cool. And especially when you see this paired with like optical measurements and telescopes and stuff, and similar missions are the ones that are looking for like spectroscopic signals of molecules out in space, and they're looking to try to discover like what are all the molecules that exist in it. Like there's literally so much to explore out there. There's so much of it, and I don't know, that stuff always just has made me very excited.
LIGO, okay. And are they're based in US?
Yes, there's actually multiple interferometers now, and so they actually now have I'd like to say that there's 3, maybe 4 throughout the world. And what's really cool about that too is like, they can share information, be like, oh, we're picking up something, on this side. And so then the other systems can make sure that they're seeing the same event too.
Okay.
If you're looking for a gravitational wave from black holes like light years away, you better hope that all of the ones on Earth are going to see it. So there are multiple now, but there is one that's in the US.
Okay.
Yeah.
And like you said, their specialty is sort of like in that laser technology and like...
That's definitely the technological, yeah.
Oh, okay.
Because they're using kilometer-long laser pathways with super stable mirrors. Like, it's really incredible technology. But then, like, the application is detecting gravitational waves, which is much more, that would be more of like a general relativity field of physics. It's basically asking these questions of like, how do we actually test the way that like light and gravity like interact with each other? And black holes there's like a lot of things we know about them, and there's far, far more that we don't. And so trying to like use what we do know to investigate more about them, like that's kind of more the applications. But also the technology to make it work is crazy. A lot of really, really good lasers.
Gotcha.
Yeah.
And I know you said you're in like the physics department there, and specifically with ion trapping research there. But is this sort of under the umbrella of like theoretical physics, would you say, or would you say it's something else?
Yeah, well, I think it is an experiment. So in that respect, it's definitely experimental physics. But, there are definitely some research that's more trying to understand like these, what we would call a grand unified theory of physics, or trying to understand more basic models of like things like gravity and light and different forces that are very foundational and important to all of physics. And so in that sense, you could kind of call it more fundamental or maybe particle physics. But the LIGO itself is definitely experimental.
What you're into is more specifically experimental and not theoretical physics, right?
Yeah, I'd say so. I think you can look at any project and, you're going to have some calculations and some coding and some like literally turning nuts and bolts. So all projects are a little bit of everything now. But yeah, I'm definitely more of an experiment. I'm definitely an experimental physicist.
Gotcha.
Yes.
And do you think that's more interesting too? Like in comparison to like too much like heady information type research?
I think for me it comes down to like wanting to touch the science. Yeah. Because it's not a fair split either between like, building stuff and pen and paper, because like a lot of the like particle accelerator type of physics or physics like at LIGO, these big facilities don't really get touched that often. At least that's not the goal. The goal is, you make these upgrades and then you like let it run for a long time and collect data. So then a lot of what even experimental physicists are doing are working at a computer, they're modeling, they're fitting data, they're trying to understand how to characterize noise, they're trying to do good statistics. And this is the type of science I did a bit in undergrad. And even though I liked the concept of what we were doing and it was, interesting in theory, I found that I wanted to like actually be working on with my hands on the physics. And that's kind of what moved me more towards the physics I'm in now. But every field has people that are working much more on either like more pen and paper calculations or a lot of computational work where you're trying to model really complicated systems. So that you can understand, if this is the basic physics principles, but we add all of these complications, are we getting what we expect out of it? And this this is very important to be paired with like experiment. The two together are part of what helps us understand what we're learning and what we're seeing. I think the big reason I wasn't interested in theory is I think I just wanted to work with my hands.
Fair enough.
Yeah.
Touching the science, right?
Yeah.
Is I think so important, and I think that's how a lot of people are drawn to science in general, is getting to see what you can do with it, how you can shape and mold it. Whereas I'm not trying to discount the theoretical at all, because it's very, very important to understand, the foundational concepts behind it in order to move forward. But yeah, it's just it's interesting what people are drawn to, whether it's like the experimental side or the theoretical side. So I think that's really cool.
Yeah, thanks.
The experimental side. So I want to move into like more of like the relationships within like a PhD process, because like we said, PhD process is such a long time, right? Like for you, you said it was like 6 or 7 years or something.
Yeah.
For others, it can be more, it could be less, but either way, it's a long period of time. And like I think, especially from what we've seen in the past couple of years, going through like the pandemic and everything, and how that impacts people in terms of like their mental health. I just want to ask, like, what do you think, like, being in, like, how do you think it's been so like helpful to have like close relationships around you, whether that be family, whether that be like significant others, whether that be, you know, like just like a healthy relationship with professors or anything like that?
Yeah, definitely. It's a really incredibly difficult thing to do without support. Like PhD is, you know, I've heard lots of different descriptions. One of my favorites is like it's, you know, a trial and working on the same thing that doesn't work for 6 years. And there's a lot of challenges, some that need to be there, some that don't, in graduate school that make it a really tough experience. And I think, you know, there's plenty of days I've finished the day just completely exhausted, like wondering what I'm doing, why am I here, like, you know. And I think relationships, just personally, I've seen have been really important to that. I have multiple friends that have been very encouraging throughout the years, and my parents have always been really supportive of me being in science, and that's been a big deal. So I think I know I couldn't do it without that support, and I don't know how other people would either. I think it's just a very difficult. You have to be really stubborn.
Yeah.
To kind of keep going at the same problem day after day. Not really paid very well, with varying degrees of technical and professional support. I think that just really varies on the group you're in. And so I think at some level you have to really want it, and you have to have people around you like letting you know that, you know, you're doing something with your life. It's not just being thrown into the void. And I have also been particularly blessed because my husband is in the program as well. Yeah. And we met in the program and got married 2 years ago. And, you know, both as a friends and with multiple other friends in our cohort, but then also just as like, you know, that incredibly special person. Like, it's very, very handy to have somebody who really understands like a lot of the difficulties of that process, who can kind of, you know, be there for you, and you can be there for him as well. So. That's
really special, because now, like, it's so great in general to have a soundboard when you come home and you want to like talk about the problems and the conflicts that you're going through. But now in this case, like, they actually know, like, your significant other actually knows like specifically what you're dealing with and like what you're having troubles with to like a really clear level of detail. Yeah. And I would imagine like that's really awesome to have.
Yeah. And thankfully, I think, you know, there's varying degrees of detail because we are in 2 different projects as well. So there's some things I can say like, oh, this broke, and he'll be like, tell me what that means. And I'll be like, great. Or he'll come back and say like, oh, we got this lined up. And I was like, and that's good. Because there are definitely certain aspects of our projects that not either of us understand, which I think is probably good for us. I think otherwise we'd probably be telling each other how to fix each other's problems. Yeah. And it's kind of nice that we can't do that. But there is a lot of overlap in our, you know, the skills we've developed in the critical thinking, the tools that we use. And there's definitely a lot of empathy and understanding for like the system we're in, how to navigate, you know, big decisions, discussions with your advisor, like working with lab mates, you know, even the system of the building and institution we're working at. And so all of that is incredibly helpful. Yeah. So I feel like we're like right in the sweet spot where we understand all the things that we probably should help each other with, but we don't understand the things that we probably would be better off just letting the other person troubleshoot themselves.
Sure. Yeah. Like mentally, it's already so taxing. Yeah. Right. And then so maybe you try to find an outlet like running to like physically. I don't know. It depends on the person how physically taxed they want to be. Yes. But I don't know. There's something about like when you're mentally taxed
Yes.
and you're not moving throughout the day, that you want to move and you
Definitely.
want to your varying degree, like however much you want to put into
Yeah.
like that physical taxation as well.
Yeah. Yeah. And what is interesting is in the lab, I do actually spend a lot of time on my feet. And so in that respect, I can come home physically tired, but there's a difference too, because at least for me, running feels a lot more directed. And there's like, you go out, you hit a certain number of miles and you come back and like you have gone that distance. You meant to go that distance. Like there's so much more intentionality to that like physical nature of running. And it definitely, I think, shifts the attention from, because even if you're on your feet all day in the lab, you're definitely way more exhausted by the thinking and the problems and maybe even some interpersonal conflict and such. And so for me, I think definitely running balances that out quite a bit and just feels like you're kind of able to move, maybe even like sprint out some of the stress, throw some strides in there. And I think for me, especially, there have been some very hard days where like runs afterwards have been very helpful for me.
But I think there's like, it's very helpful, but I think there's only so much that it helps. Like if you just are solely relying on a physical outlet, to where we come back to sort of that community aspect.
Yeah.
Family, significant other,
Absolutely.
whatever, right? That I think having that support and having like be able to do that too, I think sort of like being well balanced in that way is like what keeps you afloat.
Yeah.
Very well.
And that's part of what the hard lesson of being injured in 2020 was for me, is I was definitely at a phase of my life where I was relying too much on, running and physical activity as an outlet. And so when all of a sudden it was gone, I had to like do that introspection and reordering of my priorities to really be like, where am I actually getting my rest and my peace? And I think that is really important to keep your eyes on, because I think as work and athletic activities can really quickly become like the most important or identity defining part, and they are things that are like especially prone to failing us, like things breaking in the lab to getting injured. Like it's just so fragile, and so I think you're right, like that community aspect, and for me, and additionally faith, like that is much more the foundation. And these other things are really good. They're good tools. Running is a really good tool, but it's to try to be careful not to make it more than that.
Yeah,
for those reasons.
For sure.
Yeah.
And no, you talked about like the marathon there, but do you have any like desires at all to go farther, like to do like those long? You said you did some ultra running in the past, right? But not 100 miles, right?
Probably not.
Any thoughts on that?
Yeah. If you got to take a nap to get through it, I'm not interested.
Fair enough.
Partially because I'm not very good at napping. On a more serious note, I think at this stage of life, it's been sort of like whatever I can do while there's still daylight has kind of been my line. At some point, I might be interested in going further, but especially when you start talking about things that take 24 hours or longer. Yeah. I mean, people talk about like hallucinating and, crying and vomiting like it's great. And it's like, no, it doesn't really appeal to me. I feel like I can enjoy a lot of mountain without quite going there.
Yeah.
That being said, I know a lot of people have really enjoyed those really crazy long distances, those like 24-hour plus races. And I'm sure they are finding something really great about it. Maybe a 50-miler at some point. But probably not farther than that. Yeah.
I'm with you there. You there. I only ask because I know there's a lot of people here that is like their purpose here in Boulder is like to run really long distances.
Yeah.
But I myself like don't really see anything beyond 26.2 miles, which is the marathon. Because just again, like the more mileage that you have to prepare for, like the more work that it goes into it.
Definitely. Yeah.
So.
Yeah, for sure. And I do think what I have enjoyed about the ultras is honestly the trail running aspect of it. It isn't necessarily the distance. It's more like what is pretty cool is as you push, 15, 20 miles or more on trails, you cover a lot of ground. Yeah. Like I've done backpacking loops that I've never backpacked because I ran them in one day. And I think that's the part about trail running and ultras that is appealing to me is it's like the distances that would be really hard to enjoy hiking and backpacking, and that part of the mountains that can be really hard to access is like how trail running can help me access some of those. So if I can do it without running 100 miles, which is most everything, probably not do it by running 100 miles. So yeah, but a lot of people enjoy it, so I'm glad they do.
Fair enough. Awesome. Well, I think that's it for me.
Cool.
Unless there's anything that I've missed. But
great questions.
If not, yeah, thank you so much for coming. And yeah, I just really appreciate your time and getting to have this conversation.
Yeah, of course. This was fun. Thank you.